In Lesson 3-1, we will be discussing exponential functions. In video 3.1.1, our learning target is for students to be able to evaluate, analyze, and graph exponential functions. An exponential function is a function where x, our independent variable, is an exponent or a power. An exponential function with base b has the form f of x equals a times b to the x power, where x is any real number, and a and b are real number constants. So a and b are not variables, they are constants or numbers, such that a cannot equal 0, and b is positive and cannot equal 1. So here's the thing. If I'm looking at the function f of x equals a times b to the x power, a cannot equal 0 because if a was 0, then the entire function would be f of x equals 0. And b cannot equal 1 because 1 to any power is just going to stay 1, and we would just end up with a constant as well. So what we're looking at here is that b has to be positive as well. B cannot equal 1, but b has to be positive. And so what we're looking at for some examples here are f of x equals 4 to the x power, f of x equals 1/3 to the x power, f of x equals 7 raised to the negative x power, or the opposite of x. Some non-examples, f of x equals 2x to the negative 3. That is considered a power function, not an exponential function. Remember that an exponential function, the x variable has to be part of your exponent, hence why it's called an exponential function. F of x equals 1 to the x is not an exponential function, even though x is a power, because our base b is equal to 1. Right? The base is the number that your power is attached to, and that b value can never equal 1. If you think about this function, it's not exponential because 1 to any power, 1 squared, 1 cubed, 1 to the 4th, 1 to the 5th, no matter what we plug in for x, our outputs or our y values are always equal to 1. That's an example of a constant function where x changes but y stays the same. And then this example here, f of x equals 5 to the pi, power of pi, is also going to be a constant because 5 pi is a number, and so then we're just saying y equals a constant number, which is 5 raised to the pi power. In example 1, we're asked to sketch and analyze graphs of exponential functions. In part A, we're asked to sketch and analyze the graph of the function f of x equals 4 to the x power. We need to describe its domain, range, intercepts, so x and y intercept, any asymptotes, end behavior, and where the function is increasing and decreasing. So we have to give the intervals where the function x is increasing, or the values, give the x values where the function is decreasing. So remember, increasing and decreasing, we're describing where the y values are increasing and where the y values are decreasing, but when we write our interval notation, we use the x values for which the y values are increasing or y values are decreasing. So here's the deal. You can type this equation into your equation editor on your calculator and type in y1 equals 4 raised to the x power. So it might look something like on your graphing calculator, depending on what version you have, might look like this, or it might be typed in just like this. When you type in this little caret to raise the power, it might automatically move the x up for you. Now, what we want to do, we can graph on a standard window, so you can use Zoom option 6, and you can see the graph of the function on a standard window. Now, what we want to do is evaluate the functions for several x values in the domain. We can use whatever we want for x. We can use any exponent we want. X can be a negative, x can be a positive, x can be a fraction. In the table here, they've used the integers -3 to 3. So if you wanted to set up if you wanted to view the table that they have right here, you could go to your table setup. You would want to start your table setup at your start at -3, and you'd want your delta table to be 1. Okay, because their x coordinates here are going up by 1. Now, since our change is 1 here, our change in x is equal to 1, what we're going to see in our y coordinates is the outputs for various x inputs. So if x is -3, we would say 4 raised to the -3 power. That would give me a y value of 0.02. And if I plugged in -2 for x, 4 raised to the -2 power is 0.06 as a decimal. 4 to the -1 power is the same as 1 over 4 to the first power, and that would give me 1 over 4, which is 0.25. Anything raised to the 0 power, anytime your exponent is 0, your output is equal to 1. 4 to the first would equal 4. 4 squared would equal 16. 4 cubed, 4 times 4 times 4 is 64. So these are the ordered pairs, and then you can plot these ordered pairs and use a smooth curve to connect those ordered pairs. Now, this is what your graph should look like on the screen here. A smooth curve. If we plot those points that were in the table on the last slide, this is what our graph should look like. Now, it wants us to analyze the graph. Now, because we were able to plug in whatever we wanted for x, x was not part of a denominator, nor was it underneath a radical, we can plug in whatever we want for x, which means our domain is all real numbers, and using interval notation, that is -infinity to infinity. Now, because our exponential function is only graphed in quadrants 1 and quadrants 2, 4 raised to any power. Doesn't matter if this power is negative or positive or a fraction. Our output or our y values, no matter what we input for x, is going to always be in the first and second quadrant, which means that y is always going to be positive or greater than 0. So our range is going to be 0 to infinity. You can see that our horizontal asymptote on the graph approaches 0 but never actually equals 0. There is no value for which I can plug in for x and get an output or a y value of 0. Our y-intercept is found by plugging in 0 for x. If I say y equals 4 to the 0 power, anything raised to the 0 power is 1, so our y-intercept is equal to 1. We have no x-intercept because we approach the x-axis but never intersect it. So there's our asymptote. Our horizontal asymptote is the x-axis. Our end behavior, because we have a horizontal asymptote at the x-axis, we'll say our left end is approaching -infinity. Left end is approaching 0 here. As I go towards -infinity, y is going to approach 0. But as x approaches infinity, the graph goes up infinitely, and therefore our right end behavior is infinity. Our right-hand limit is infinity. Increasing, the function is strictly increasing. The y values are constantly going up from left to right. There's never a turning point. The slope is never negative. The y coordinates never decrease. Therefore, our function is always increasing from negative infinity to positive infinity. In part B of example 1, we're asked to sketch and analyze the graph of f of x equals 5 raised to the negative x, or opposite of x. We need to describe its domain, range, intercepts, asymptotes, end behavior, and where the function is increasing or decreasing. Now, evaluate the function for several x values in its domain. Okay, if we're going to graph the function f of x equals 5 raised to the negative x, you could type in the function f to the opposite of x, or negative x, and graph on a standard window. If you did the first example, part A, your table setting should already start at 3, and your change in your table should be going up by 1s. And we're looking to connect these dots with a smooth curve. Now, here's the thing with our function here. I'll just talk about this for a second. 5 raised to the opposite of x, if that's my function, and x is negative 3, then I'm going to say 5 raised to the opposite of negative 3. Okay, x is negative 3, but there's this extra negative sign out in front. And so when you input your x value, if your x value is negative, since you have this negative sign already in front of x, that double negative becomes a positive, and I end up with 5 cubed. So 5 cubed is equal to 125, hence why when I input negative 3 for x, my output or my y value is 125. And when I plug in negative 2 for x, I get 5 squared, which is 25. 5 to the negative 1 is the same as 1 over 5. Actually, when I plug in negative 1, I end up with 5 to the first, which is 5. Anything raised to the 0 power, 5 to the 0. 0 is neither negative or positive, so the opposite sign or the minus sign in front of x doesn't matter there. And we get 5 to the 0, which is just equal to 1. 5 to the first is equal to 5, in this case 5 to the negative 1. 5 to the negative 1 is 1 over 5. 5 to the opposite of 2, which is 5 to the negative 2, which is 1 over 5 squared, which is 1 over 25, which is 0.04. And 5 to the negative 3, or 5 to the opposite of 3 here, is going to be 1 over 5 cubed, or 1 over 125, which is 0.01. Plotting the points from the table on the previous slide, we should end up with this graph right here. And your graph is decreasing constantly, because as we move from left to right, the y values are falling or decreasing. I shouldn't be crossing the x-axis there. We're going to approach the x-axis but never intersect it. So we're decreasing from negative infinity to infinity. And we have, since we're approaching the x-axis but never touching it, our horizontal asymptote is the x-axis. Our domain for the function 5 to the opposite of x, because I can plug in whatever I want for x, x isn't part of a denominator, neither is x part of a radical that has an even index, like a square root. Since x is not under a square root or a fourth root or a sixth root, we don't have to worry about any restrictions on our domain. So our domain is all real numbers. Our function is continuous. I can sketch this graph without lifting up my pen or pencil. My range here is going to be from 0 to infinity, because no matter what I plug in for x, for any exponential function, any basic exponential function that is growth or decay, your range is going to be from 0 to infinity. Our y value, since we approach the x-axis, our least y value is 0, and our greatest y value, since our function is going towards infinity, as the x goes towards negative infinity, my left end is pointed up, So therefore, my greatest y value is infinity. So my range goes from 0 to infinity. My y-intercept is at x equals 0. So if I plug in 0 for x, my output or my y value is 1. We don't have an x-intercept since we have the x-axis as our asymptote, our horizontal asymptote. And so we never intersect the x-axis, so therefore there is no x-intercept. And the end behavior, our right end, as we go towards infinity to the right here, as we go to the right, our y values are approaching 0. Hence the limit as x approaches infinity of the function is equal to 0. And as I'm going to the left or towards negative infinity, my end is pointed up. Therefore, as x approaches negative infinity, y is approaching infinity. In the example 1 guided practice, we're asked to sketch the graph of the function f of x equals 3 to the negative x. And we are given 4 choices for the graph of this function, A, B, C, and D. And you need to choose which graph matches the equation. I would like you to go ahead and graph this function using a graphing calculator or by hand, and then choose the correct solution. In example 1, part B guided practice, we're asked to describe the domain, range, intercepts, asymptotes, end behavior, and when the function is increasing or decreasing for the function f of x equals 3 to the negative x, which we just graphed in the last example. Go ahead and analyze this function and choose the correct solution A, B, C, or D.